So cloud computing, just like I've said, was not an abrupt innovation, but the idea was there, but it wasn't implemented because there wasn't the technological framework. So the progresses in cloud computing, starting from the early days, slowly metamorphosed into cloud computing. Metamorphosis is an English word that means that something is changing from one form into another. So it was just something like a change. Probably it was accidental. Now, the documentary evidence can be traced back to somebody known as John McCarthy in the 1960s. Now, he's the one who came up with the term artificial intelligence. But at that time, he wasn't really talking about cloud computing. So he was saying that computation may someday be organized as a public utility. Now, you see, a public utility is something that is shared. So he was saying one day computation may be something that is shared, just like electricity. You know, for electricity, you shall find that electricity is generated in different places. We have the Seven Forks Dam. We have the geothermal stations, and so on. All these are distinct units that generate electricity, and like in Kenya, they are managed by the KenGen, Kenya Electricity Generating Company. Now, after they are managed, after the electricity is generated, it is pulled together, and then Kenya Power and Lighting Corporation now distributes it, and you now pay for it as a utility. So this is what we are saying, that it may be sometimes, maybe someday organized as a public utility. So like when you have electricity, you don't care whether it's geothermal or whether it's hydroelectric, and you don't care where it is generated. The thing is that you just have your electricity without caring about the source. That is what he actually meant. Now we shall be elaborating on this later on. So the concept of cloud computing came into existence in the 1950s with the implementation of mainframe computers accessible via thin static clients. Now, what does that mean? In the mainframe computer, what happened is that the mainframe itself was one piece of machine which had a processor and it had memory. Now, for you to access the computing resource, which was a combination of the processor and the memory, you needed a keyboard and a screen. Now, why we are calling it thin or static clients is that those clients were simply input-output devices. They did not have their own processing power. So what happened is that via communication links, these input-output devices were attached to the mainframe computer. But in the mainframe, the mainframe computer did all the processing. So if you wanted to access computing power, you went to this thin client, which was just made up of a keyboard and a screen, or other input-output devices. And you could have 10 people accessing that mainframe. Now, since then, cloud computing has evolved from static clients. What we mean by static is that these input-output devices did not have their own memory and did not have their own processor. They depended on the mainframe. So we have evolved from that to dynamic ones, and then again from software to services. We shall be seeing this later on. So the evolution of cloud computing was characterized by the developments shown below. In the 1950s, we had the mainframes. Now, mainframes was the beginning of automation. So what happened is that there were certain functions that were automated, like say processing, doing the payrolls, doing the payroll for staff in an organization. So that computation of the payroll was done by the mainframe. But in that case, the mainframe was centralized. So what you do, you would find that probably we have 10, 10 thin clients accessing one mainframe processor. And all the calculation was done in the processor. Then the 1960s was characterized by the PC. Now, in the 60s, what happened is that, you know, the mainframe used tubes. And basically, these were huge, they were massive devices that used tubes, and they needed a substantial amount of cooling, and they needed a big building. But later on, we moved away from tubes to integrated circuits, which were chip microprocessors, where you would have a processor and you'd have a memory on a chip which was quite small. Now this reduced the cost. So what happened is that instead of depending on one centralized hardware, using the chips, we could have all the functions of the mainframe being put into one piece of hardware, which was called the personal computer. So in the 60s, because of this chip microchips, what happened is that the PC was born. And once the PC was born, people saw the importance of computing, and there was a demand or a rise in demand of personal desktops. And these personal desktops were now decentralized because the computing was the computing was localized. In other words, individuals could own their own computing power. Then the 1990s was characterized by what is called client-server architecture. In the client-server architecture, we now introduced the concept of the server. Now here we have a PC, which has its own memory, it has its own processor, it has its own input-output. But you could do localized computing. But there were some services which you could access on the server, which was in a way similar in operation to the mainframe. Then the 2000s was characterized by what is called the hosted environment. And the hosted environment, the IT infrastructure management was outsourced. So you would find via something known as you would get services from outside. So you didn't have to host these services on your PCs. Then beyond 2000, we had now the emergence of what is called as a service. In other words, instead of you purchasing your own software, what you did is that you purchased a service. So you didn't have to purchase software and put it onto your and load it onto your PC. What you did is that you started looking for these services. So basically, what this course is all about is about the cloud. But before we talk about the cloud, we shall see, because I've said cloud computing was people didn't set out to come with it. It was as a result of evolution. So this is what we are going to look at today. So we had various advances in technology that led to cloud computing. We had advances in hardware, advances in internet technology, advances in distributed computing, and advances in systems management. So this is what we are talking about. Cloud computing is an intersection of advances in hardware, distributed computing, internet technologies, and systems management. Now, what was it in hardware that caused that led to cloud computing? In hardware, we had hardware virtualization, and we had what is called multi-core chips. Then in distributed computing, we had technologies known as utility and grid computing. Then in systems management, we had autonomic computing and data center automation. And in internet technologies, we had what is called software-oriented architecture, Web 2, web services, and mashups. So we shall be looking at all these technologies that led to what we now refer to as cloud computing. Somebody. Okay, so we've said these technologies came together to come up with what is called cloud computing. So we shall be looking at each of these technologies that led that combined to come up with cloud computing. So some of these technologies, in other words, some of these things were initially tagged as hype in the early stage, in the early stages of development. You know, hype is when the word hype is used when people talk so highly about something, but it doesn't happen, or when people overvalue a technology more than it actually happens. But as happens, you know, academia, people in the academic world and in the research world, they are always trying to explore things. Now, some of these things may work, and some of them may not. So, but that is what is research. Research is pouring into the unknown, trying to see, trying to find out what is this that we don't know. So, I mean, if you don't know something and you want to know about it, finally it may be of value or it may not be, or it may not be of value. Now, what happens is that researchers try out new things and try. Now, sometimes this knowledge is successful. Now, the moment it becomes successful, then we do specification and standardization. Now, the moment a technology is discovered, uh, now I'll be talking about this later on, something like grid computing. Researchers were trying to see whether computing services can be treated as a utility, or whether computing can be pulled together. Now, grid computing didn't pick up, and it stopped there. But as we shall see, cloud computing came out of the idea of grid computing. Now, cloud computing has picked up. Now, the moment a technology picks up, then standards now come in. And the moment standards and specifications come in, then it's commercialized. Now, this is why you find that these days people treat cloud computing as an accepted technology, because it's becoming standardized. And once it's standardized, then it can have commercial applications. So standardization and specification leads to maturity and wide adoption. And this is what has happened with cloud computing. Now, since then, computing technology has gone through various phases of development. Hardware and communication technology have progressed. The internet has changed. Internet has now changed from what it was initially envisaged to do. Now, hardware and communication technology, I'm sure you know that has changed. Then these days, we have what is called web-based software architecture. Now, web-based software architecture has matured. There's something that we call software-oriented architecture, which we shall be looking at later on. So this is how cloud computing grew. In the early 1960s, we had the mainframes. Now, like I told you, mainframe was a single piece of hardware that had a processor, and it had the memory. Then we had input-output devices. In other words, we had a keyboard, and we had a screen. Now, initially, the mainframe was produced to do a single task, and this single task was mainly done by a single user. So you would find that you spend so much money to purchase a piece of equipment that is only going to do the payroll. And that was in the 1960s. So, but of course, with advancement in software and advancement in operating system technology, people say, I mean, it's expensive to purchase to purchase a piece of hardware that is only doing one task and is being used by only one user. So, is it possible to use this piece of hardware to do many tasks and to be used by many users? Now, this happened in the 1970s, where we had what are called multi-user mainframes. Now, in the multi-user mainframes, it was both multitasking in the sense that for the same piece of hardware, using software, you could do different tasks. So what the software did is that depending on the tasks that you wanted it to do, the software gave this piece of hardware different instructions. Now, depending on those instructions, different tasks could be done. But again, what is the point if these many tasks are only being done by one person? Isn't it also possible to have this same hardware being used by many people to do many tasks? Now that is what was called multi-user multitasking. So in the 70s, the mainframe started being multi-user multitasking, many users and many tasks. Now at that time, there was an operating system that was called Unix. So Unix, when loaded onto the mainframe hardware, would allow many users to do many tasks. And it was able to do this by using time slices. Now, what happens with time slices is each user is given a slice of time. Now, when that time elapses, it transfers the control to another user, and it kept doing that. Now, once you are given your time slice, then you could do the task that you wanted to do, which was not necessarily the same task as your neighbor wanted to do. So what happened is that the Unix operating system would give one user a time slice. Now, during that time slice, that user would do a unique task allocated to himself. Now, in the 80s, there was advances in the microchip technology. Now, this allowed people to own PCs. I mean, they could have their own processor, their own memory, and their own input and output devices. So, in other words, you now did not need to share as a central processor. You had your own processor at your desktop. So and this happened in the workplace. So you could do your own computing. Now, an example is that I've talked about the Unix. What happened is that now the Unix operating system was changed into what is called Linux. Now, Linux, the difference between Linux and Unix is Linux is single user multitasking. Unix was multi-user multitasking. So Unix was initially meant for the mainframe, but later on it was when PCs started appearing on people's desktops, then Unix was configured to become what we now refer to as Linux, and that's why you'll find that a lot of the commands that are used in Linux can also be used in Unix. The only difference is that Linux is now single user, but multitasking. It can do many tasks. Now, later on, there came what is called client-server computing. And client-server computing, you could have some computers which could be accessed by, you could create a network, and you have certain computers which could do certain specific functions, like, for example, storing, for example, accessing the internet, for example, managing printing. So what you do, there are certain tasks you could do on your personal PC, on your desktop, but there are some things which you would give the server. So in other words, the server was just like a mainframe because it was servicing many PCs, and that's why it was called the server. So that was the rise of client-server computing, which happened in the 1990s. Then in 1995, there was the growth of the internet and the World Wide Web. Now, of course, you know that the internet is a network of networks, and the World Wide Web is a network of documents. Now, some people try to interchange the two. The two are not the same. The internet is a network of networks. The World Wide Web is a network of documents. But of course, we cannot have the World Wide Web if we don't have the internet, because the World Wide Web depends on the internet. Now, from there, in around 2005, we moved to the cloud, the social media, and mobile devices. And now this is where we are at right now. So what is happening is that we are just trying to advance this technology right now. In other words, to make it better. So this is how the cloud computing evolved from the mainframes to the cloud where we are at right now. So the emergence of cloud computing is closely linked to the maturity of many technologies. We have looked at that. So we shall have a closer look at these technologies. Now, what are these technologies that evolved to create cloud computing? Now, the first thing is the mainframe architecture. Now, initially, I mean, the mainframes were the beginning of computing. Now, mainframes processing the payroll involved numbers, and it involved some computations. Now, you know, human beings are prone to errors, and that's why computers were brought, and computers are fast at processing, doing number crunching compared to human beings. Human beings are good at tasks that require common sense and creativity, but tasks that are repetitive and require fast processing, human beings are not very good at that. So that's why the mainframes were introduced. But basically, technically, the mainframe architecture introduced what is called time sharing. Remember, I've said that the mainframe had it had memory, and it had the processing power. Now, but what happens is you want many people to make use of that processing power, which was quite fast. So what happens is that you give these people different time slices, and this is what I was telling you the Unix operating system was doing. Now, in the original mainframe, what happened is the clients, the thin clients, were simply input-output devices. They didn't do any processing tasks. All the processing was done by the mainframe. And what the mainframe did is that it just gave the different clients time slices. It gives you 10 seconds. After 10 seconds, it transfers control to somebody else for the 10 seconds. Now, once it transfers control to you, then you have full access to the processing power. Now, this meant that as the number of people increased, the latency also increased. So later on, the concept of intelligent terminals was introduced, where this input-output devices was given some processing power. So this relieved the load from the load from the mainframe to the clients, and that is why we are calling them intelligent terminals. Intelligent in the sense that they had some limited processing power, and they could interrupt the mainframe. So you know, in the original mainframe, what happened is that you are given a time slot 1, time slot 2, time slot 3, and so on. So you accessed computing power sequentially. But when intelligent terminals were introduced, they had some limited processing power. There was some limited tasks they could do. But in addition to that, they could interrupt the mainframe if a critical task arose. So the time sharing was not sequential because they could do interact depending on the criticality of the job. Then later on, with the improvement of microprocessor technology, there came the PC revolution. In other words, people, rather than having computation being done centrally, computation could be done locally. And people started having PCs on their desktops. The microchips were smaller, they didn't require substantial cooling, and so on. So the PC revolution had the scope for computing everything locally. Now, later on, you, you know, when you are in an organization, you want to share information. So yes, it's possible to do computation locally, your own computation. But supposing you want to transfer your result to somebody else, then you will need the network. So later on, PCs were networked, and this led to the emergence of direct peer-to-peer communication. Simply means this. You know, centralized computation means that we have a master, and then we have what are called slaves. But in peer-to-peer, all of you are equal. You only share, you can do your own computation autonomously. But if you need to share information, then you use the network to transfer your result to somebody else, or somebody else can transfer the results to you. So this is what we refer to peer-to-peer communication. Then, of course, once that happens, people are generating more and more data. People are seeing the value of PCs. Automation is increasing. In other words, a lot of things are now being done automatically. Now, this brings in a lot of data. So because now the PC is doing most of the tasks which were done manually, which means a lot of, you will need to transfer data and you'll need very fast networks. So once the automation increased and a lot of data was being generated, then the technology had to move. In other words, the networking technology, the data transfer rate had to increase. So you find that there was now a lot of research into increasing the speed of transfer of data. So this is what we mean by fast network communication, which led the way for distributed computing. So in distributed computing, what happens is that you can locally do your computation and then transfer your results to another computer and so on. No, once that was possible, once distributed computing was possible, then came what is called cluster computing. Now, in cluster computing, we had clusters of computers. Now, what we mean by clusters of computers is that we had computers which did similar tasks. So because of that, when a job comes, you could, in cluster computing, we had what is called a cluster head. We had one computer which was in charge of all the other computers. So once you have one, if you had a job, you put it to you sent it to the cluster head. What the cluster head did, if the cluster was made up of 5 computers, it will divide this job into 5 tasks, sorry, into 4 tasks, and it will distribute the 4 tasks into the 4 computers. Now, these computers do these tasks independent of each other. Then once they have done that computation, the cluster head aggregates. Aggregating means putting all the results together and giving one output. So, and of course, that made work faster because a job comes split into 4. These computers do the computation independently. Then the cluster aggregates and it gives a unified result. So cluster computing led to the concept of creation of what is called a resource pool. Now, in cluster computing, clusters had to do similar tasks. Now, from cluster computing, then we went to what is called grid computing. Now, grid computing is similar to cluster computing, but the only difference is that in grid computing, we don't have a cluster head. All the computers are equal, and all the computers behave autonomously. And the computers could do heterogeneous tasks. So in cluster computing, the tasks, the computers had to be homogeneous. Homogeneous means that they only did similar jobs. Now, heterogeneous means they could do different tasks. So grid computing was a good concept. And in grid computing, just like I'm saying, the concept was to try and make processing fast. So what happens is that if a job comes in the grid would distribute it to different processors. The processors could work on that job, and then they could aggregate. But like I've said, in grid computing, there was no cluster head. All computers were equal, and the tasks didn't have to be similar, like in cluster computing. Then later on, there was what is called hardware virtualization. A processor, you see, a processor can be very fast, and you'll find that most of the time it's idle. So people say, okay, why don't we try to make efficient use of this processor? So what they did is that they created an additional layer on top of the operating system. Now, this additional layer would make a copy of a certain function. And once it makes that copy, you would find that, for example, 5 people want to use the same software. So that software, 5 copies of that software are made, and they are distributed to these 5 people. And these 5 people will not be aware that they are using one software. It appears to them as if that software is theirs alone. Now, we shall have a section on this, so I'll skip this for the time being because it's a bit complex. Then advancement in web services, like I've said, the WWW initially was a network. The World Wide Web was a network of documents. But these days, it has changed. It's not, when we talk about the World Wide Web, we are just not talking about documents. We are talking about many other things. We could be talking about video, we could be talking about music, and so on. So the focus of the web has changed, and that is why we are talking of advancement in web services. And again, we shall be looking at that. Then we have what is called service-oriented architecture. Initially what happened is, if you wanted to do something, you would buy software, load it onto your machine, and you use that software to do that task. So what it meant is that all the time you wanted your computer to have certain capabilities, you had to have that software. But now these days, with the concept of cloud computing, we don't have to do that. What you do is that you look for a service. For example, it could be a graphics service. Instead of buying the software for you to draw, you look for the service for you to draw. Now, all that is captured under what is called the service-oriented architecture. Then utility computing. This is borrowed from electricity, like I was explaining to you about KenGen and KPLC. You find that KenGen is in charge of generating electricity, and it doesn't matter what form that electricity is generated. It's put onto the power grid. But now you buy this electricity, you pay for electricity without caring where the source is. Now, that is the same thing with computing. These days, you can get storage without caring where your documents are being stored. You can get a service like what I've explained, graphics, without necessarily having to buy the graphic software. So that is so utility computing is you treat everything as a service, but because it's a service, you have to pay for it. So that is referred to as utility computing, where computing is measured as a utility service. Then we have what is called autonomic computing. Autonomic computing is where we have as little human intervention as possible. And in this case, we use what are called agents. So, and agents are simply software programs which do certain things for us. So we try to limit the amount of human intervention as much as possible. So all these things, from where I started, all these things, these are all evolutions, because from mainframe architecture, we went to intelligent terminals, to PCs, to networking the PCs, and to improving the network. Then from distributed computing, we moved to cluster computing. From cluster computing, we moved to grid computing. Now, after grid computing, we came to virtualization, advancement in web services, software-oriented architecture came, then utility computing, autonomic computing, then finally, these all evolved to come up with what is called cloud computing. Now, grid computing was a very good concept. It was too complex. It was very complex, so it didn't catch on. Now, what has finally caught on is what is called cloud computing. So cloud computing, in a way, is a variation of grid computing. So what I shall do now is to talk about each of them in a bit of detail, though not very detailed, but in a bit of detail. So mainframe architecture, now I'm going according to my table. So where commercial usage of computing started with the mainframes around the 70s, which basically consisted of automating basic data processing tasks. For example, payroll management. So mainframes were large supercomputers that required extensive cooling. I told you they were made up of tubes, and they were highly priced that it was even difficult for business organization to maintain more than one. So one, they were huge things. They required a lot of cooling and they were expensive. So how now this becomes a problem? Yes, you have automated certain functions like payroll processing. But you see, you have solved that task. But that solution introduces another problem. You are solving the problem of automation, but you are introducing cost. You are introducing cooling. Of course, you need a big room. So what happens? How do you solve this problem? Yes, you've solved one problem, but along with the solution, another problem comes in. So how do you do it? The solution to that problem was the emergence of a time-shared resource utilization. So why not share this big, huge monolithic thing? Because anytime you share something, then you cut the cost. So that solution was the time-shared resource utilization, which was the option of multi-users sharing the same computer resources concurrently. So sharing cuts down the cost, because if you have one mainframe being used by one user, then that one user will bear that cost. Just a minute. Sorry about that. So, and of course, when we have many users sharing the same computer, these users are not in the same location, and in fact, that is the essence of sharing. You want people who are you want people who are working remotely to share the same. So this led to the advent of what is called remote access facility. So the need for multiple mainframe systems disappeared because we have already introduced the concept of a time shared resource. So organizations could access a single mainframe system from different locations using computer terminals to fulfill computing requirements. Terminals did not have any processing power and were known as dumb terminals or non-intelligent terminals. Now, these were only capable of transferring input-output data to communicate with the mainframe system, which was also called a server. Now, that is where that is the term server was introduced, because the mainframe was now servicing many users. So it became known as the server because now many users are accessing it remotely, and it is able to service them using the concept of time sharing. Now, the second one here is intelligent terminals. So there were problems, there were limitations in accessing the mainframe computer. Remember, dumb terminals, I told you, were simply input-output devices. And at that time, the mainframe was using time sharing. So what were these problems? Now, these problems were these that concurrent requests appearing from different terminals could not always be processed at the same time. Remember, in time sharing systems, you are given your time slot. If you are 10 people, your time slot is numbered. Time slot 1 up to time slot 10. So time slot 1 is given to user 1, maybe 0 to 10 microseconds. Then 10 microseconds to 20 microseconds, and so on. So supposing 5 of you had tasks at the same time that required computing, then you had to wait for your time. Appearing from different terminals could not always be processed at the same time because of that time sharing concepts. Mainframe systems always had a number limit in regard to parallel active users, and users often had to wait for a long time in the queue. So you'd find that if tasks appeared concurrently, then some people would be inconvenienced. Actually, all of you would be inconvenienced because you would have to wait for your time slot. And at that time, there was no prioritization. Remember that dumb terminals just waited to be given control. Now, after the time slot ends, that control was passed to somebody else. So you would find that a dumb terminal is being given a time slot, and yet it has no task. And yet there was another terminal which had a critical task, but it had to wait for its time slot. So the solution to this was the development of what are called intelligent terminals. Now, intelligent terminals had some processing capability and could compute some minimal tasks. So this dream turned into a reality with the arrival of low-cost microprocessor technology during the 70s. Dumb terminals were smaller and had some processing capability and replaced the dumb terminals easily. Now, these dumb terminals were later on known as client systems and could participate in partial execution of programs along with servers. So yes, the server was doing most of the computing, but dumb terminals could do some low compute intensive tasks. So what happened is that with intelligent terminals, the load was released from the server. So in other words, the computation became faster because the server didn't have to do all the processing. Now, this was the beginning of what is called client-server computing. Now, just like I mentioned a few minutes ago, in client-server computing, the client has its own memory and its own processor. But there are certain specialized tasks that it sends to the server. Now, for example, you could have what is called a print server. A print server, all PCs don't need to have their own printers because most of the time the printer is free. So what a print server would do is it would manage the queue of print jobs. So it's dedicated to do that. So with the concept of intelligent terminals led to what is called, was the beginning of what is called client-server computing. So intelligent client systems promoted the concept of offline processing by taking part in the execution of programs along with servers. So offline processing simply means that there are some tasks which could be done locally without the need of accessing the server. So any questions so far? Any question? Okay. There's nobody who's asking. So next we move to the personal, the what are called the PC revolution. Now, offline processing by intelligent terminals reduce load on the servers for some time. But with increasing processing demand, this was still inadequate for the performances of large organizations. During peak hours, when client terminals were flooding the server with tasks, the response time were increasing drastically due to the bottleneck problem. Clients' systems had very limited processing capability, and technologies were looking to take the next step. Now, what happened? Even though intelligent terms reduced the load on the mainframe, because they could do some limited tasks. Now, but these tasks were very limited. And remember that as technology improves and people see the value of it, they demand more. So people were demanding more from intelligent terminals. But you'd find as the number of people increased, the response time increased. In other words, it took you longer to do a task because you are still dependent on the mainframe. There are certain tasks that had to be done by the mainframe. So what happened? Researchers were researching to make the intelligent terminals powerful so that they could reduce the relying on the mainframe computers. So what happened is that there was a lot of research into increasing the processor speed and reducing the cost of the processors. So what the solution to the bottleneck of processing during peak times was to do more research into microprocessor technology. So, so the solution to this was economical client systems with more processing capability. So in other words, try as much as possible to reduce the reliance on the mainframe computers. And how do you do that? You want to make these intelligent terminals even more intelligent. And how do you do that? By doing research into what is called microprocessor technology, so that you now put even more processing power in the intelligent terminals. Now, this led to what is called the personal computer. So what is this microprocessor technology? This was small-sized, powerful processor, microprocessor, along with a little main memory and limited input. Output were embedded in chips which could be produced at a relatively low cost. This was considered as one of the salient stepping stones towards the future age of computers. It created the scope for manufacturers to produce general purpose computing machines for users. So these machines were later on called personal microcomputers, and later on the name evolved to personal computers or personal PCs, because the more the technology improved, the higher the processing power, and you find that the processing power starts matching the speed of the mainframe computers. So you find that as technology evolved, there was less and less dependent of these intelligent terminals on the mainframe computers. So, in other words, we are now making the intelligent terminals to be more and to be more and more to move more and more closer to the mainframe computer, or to make it more and more similar to the mainframe computers. So this this less expensive computers revolutionized the computing world, or in other words, offline or local processing by clients combined with this time-shared processing server in a client-server model could now be implemented together as on a single system. So everything could be computed locally. So PCs, remember, initially mainframes were used to use tubes, and then later on they were using microprocessors. Now, these microprocessors were becoming smaller and even more powerful. So in other words, what we are saying is that we are now moving the processing power away from the mainframe to the desktop. So that having been done, now we are talking about what is called offline processing. In other words, you could process your tasks locally. But as happens with computing and with data, you find that most times you don't produce data for yourself. Most times you are producing data for somebody else. So, offline simply means you are doing your data locally, but you'll need that data to share. Now, for you to share, then you'll need these PCs to talk to other PCs. Now, this led to the concept of a network of PCs. And for big organizations, you'd find that we'd have multiple PCs in different offices. But the problem with this is that PCs could not communicate directly because the machines were situated at a distance from one another. Now, computers installed at different offices within an organization were functioning independently. So here we have PCs which are produced locally, but in an organization, it's called an organization because there's the need for data sharing. But remember, PCs was a solution to mainframe computers. Now, but PCs are mainframe computers were designed in such a way that they needed some networking, because remember, in a time-shared environment, the input-output devices could be a distance apart, but they need the processing power of the mainframe. So when mainframes were designed, there had to be some networking. But we have moved away the processing from the mainframe to the PCs. So we were concentrating on dealing with the problem of the mainframe, the problem of compute. So once we have solved that, we have now forgotten about the networking. So now networking now becomes the next problem. So for mainframes, networking was natural because the mainframe couldn't operate without that link. But PCs was as a result of solving that problem of the mainframe computing, the time sharing concept. So the next problem now becomes, how do you network these PCs? So technologists working on network communications have succeeded in establishing interactions between systems situated a little distance from one another. So they start working on they start working now on improving the network links. Now, of note, even though here we are talking about technologists, networking, the networking of PCs was in a way influenced by what is called the Cold War. Now, what happened during the Second World War? I mean, after the Second World War, countries were a bit jittery about each other. So countries started signing agreements on protecting each other. Like Europe, America met, and they met under what is called the North Atlantic Treaty Organization, where they said, let's sign a pact that if any of us is attacked, we shall pull together and retaliate together. So what was called the Western Bloc Alliance. When the countries in the East, Russia and the rest, saw that NATO had been formed, they met in Warsaw, Poland, and they formed what is called the Warsaw Pact, which was similar to the NATO Alliance Pact, where they said, if any of us is attacked, then we shall pull again and retaliate. Now that was the beginning of what is called the Cold War. Now, why it's called the Cold War is you are so afraid. You always live in fear. That and of course, again, technologically, the nuclear warheads were being developed. So you are always living in fear that we may be attacked. We may be attacked. So why I'm talking about this is that the networking of PCs is directly linked to that. Now, DARPA, an agency in the US Army, is one which started by saying the way we store our data locally, you find that we store a lot of data in one place. Now, supposing the Warsaw Pact, any of the nations in the Warsaw Pact bombs this place where we store data, what is going to happen? We will lose our data, and we know that information is power. So what DARPA did is that it sent out a call where it asked researchers, companies, and so on to find a way of networking PCs. Remember, now I've said the PC was as a result of addressing the limitations of the mainframe computer. Now, we have data on the desktop, but the problem is that we are storing data in one place, and that one place is what DARPA was fearing, that if we store all our data in one building and that building is bombed, then our loss will be great. So is there a way we can distribute data in different places, or from one building or one PC to the next PC? So they sent out a request for people to come up with a network. So this network was born, and at that time, different organizations, different researchers were working to come up with different networks, and they came up with many different networks. Now, all those networks were what are called proprietary networks, because Ethernet came with its own network, Local Talk came with another network. We have many others, I can't remember their names, but a lot of networks were developed towards the end of the 60s. But they were proprietary in that I created a network based on my own protocols. So this is why I'm saying technologies working on network telecommunications succeeded in establishing interactions between systems situated a little distance from one another. So After that is done, yes, you can transfer data from one computer to the next by using a link. That time it was mainly electrical. But then you realize that you're transferring, the data transfer needs are increasing. So after the network has been established, after that technology has been established, the next thing is, how do we increase the speed of that network? So once the technology was there, then the next thing was increasing the speed of transmission. So this is where we now had what is called fast network communication. In other words, the technology is now existing, but you need those speeds to be high. So you start working now on increasing the speeds. So this is where we are saying that technologies became successful in transferring data through a LAN within premises with a speed at the order of megabits per second. So initially, for the local area network, the speed was in the order of megabits per second. But for the WAN, the technology could only transfer in kilobits per second. So you find that even though PCs can now, this technology to enable pieces to be connected locally or to be connected over a wide area, there were still variations in speed. Now, so remember, now we have solved the problem of the mainframe by moving to the PCs. We are now able to transfer data between the different pieces because we are now having a technology to transfer data from one computer to the next. Now, at that time, the term peer-to-peer computing came. Now, peer-to-peer is a bit different. I mean, it's called peer-to-peer because now all systems are equal. Remember, in mainframe computing, it was what was called the master-slave kind of computing because the mainframe is the main controller. The mainframe gave you permission to access it. So it was the master, and it was doing that using the time sharing concept. But now remember, in the PC, you don't need permission from somebody. You have your own processing power, you have your own memory, you have your own input-output devices. So it was now what was called peer-to-peer computing, where each and every computer could play the role of a client and it could play the role of a server as well. It could be a client, in other words, it could request a service from another server, or it could give a service to another client. So as you read, you'll find that you come across the term peer-to-peer computing. So peer-to-peer computing simply means these computers, there's none that is controlling the other. There's no master and there's no slave. They are equal. They only transfer data when there is need. So we have talked about after networking, the next thing, because of peer-to-peer computing, there was a need of faster networks because each computer, each client can now generate its own data, and you find that there's greater need for faster transfer speeds. So the next thing was now trying to improve the speeds of data transfer. Now, alongside this came the idea, because a lot of data is being generated, there came the concept of what is called parallel processing. Now, in parallel processing, multiple processors work together to solve a single computational tasks. Now, this is similar to one computer with multiple processing. So in parallel computing, what happens is that we have many processors. So if a job comes, you divide, for example, if you have 4 processors, if a job comes, you divide it into 4 parts, and you give each processor a part. Now those processors work on their parts, produce results, and then you aggregate. So in parallel processing, what happens is that you'll have the different processors on one chip. So you have different processors on one chip. So in other words, in parallel processing, what is happening is that this is happening on a local machine where you have a chip, or you have 4 processors on one computer. So we have a controller which distributes which take a job, split it into the different processors. The processors do the processing, and then the controller aggregates. Now, so of course, this reduces the process. If it's 4 processors, it reduces the processing by 4. It makes the processing time a quarter of what was there originally. So parallel processing happens within a computer. So in other words, that computer is very fast. But isn't it also possible to have, if you have a network, isn't it also possible to have these jobs being done by different computers? Instead of having one chip doing that job, isn't it also possible to have these jobs being distributed to 4 different computers? So this is what was now called distributed computing. So the difference between parallel processing and distributed computing is that in parallel processing, we have many processors in a local environment, and there's a controller within that local environment, where the local environment would be a PC. So, what parallel processing did is that it improved the speed of a computer. Now, what distributed computing did, because now we have many computers linked by fast networks, you take this job and you distribute it to 4 different computers. They work on it, and you aggregate it. Now that is what is called distributed computing. So you can see we have now moved away from the mainframe. We've gone to the PC. Now from the PC with fast networks, we've gone to distributed computing. So so the distributed computing took the parallel processing concept one step forward. It's formed one powerful computing system by combining multiple computing systems rather than having one computer with multiple processors. So this is what I am calling parallel computing, and this is what I'm calling distributed computing. So distributed computing is roughly defined as a collection of processors interconnected by a communication network in which each processor has its own local memory and other basic computing peripherals. So distributed computing basically is just having many computers, but you shall find that this work, and you shall find that a job is taken to each computer. In other words, once a job is comes, it's split into tasks, and these tasks are distributed into different computers. They compute, they give their results, and the results are aggregated. Now that is as opposed to parallel computing. So the distributing processing concept emerged as a powerful computing model. This needed frequent communication among nodes of a system during program execution. So higher speed in network communication was required. So now again, you can see the concept of distributing jobs to various computers requires that the network becomes fast. So hence the need for fast network communication. So in the 80s, LAN speeds were 100 megabits per second and WAN speeds were 64 kilobits per second. But with the time, and up to these days, those speeds have changed. So this is a model of the distributed computing environment. We have a network communication path. So this is a computer network communication path for distributing jobs among nodes. This is a node or a computer to perform a B-type task. This performs an A-type task, an E-type task, a D-type task, and a C-type task. So each of these computers has a local memory and a processing power. So we are saying each of these, what we are calling nodes, are actually PCs. Now each PC is doing a different type of task. So a job comes and it's split into various tasks, and each computer is doing its own tasks. And now this is possible because we have a network connectivity, and like I've said, now we need fast network communication because it's possible. Like I was telling you, that in parallel processing we have many processors in one computer. So what happens is that computer is very fast. But now, if you are doing parallel computing in this node, and it's very fast, and yet this link is very slow, then you've really not done anything, because now the network link is going to be the bottleneck. So that's why we are saying technology is advancing. Parallel computing is increasing the processing speeds. But you want these tasks which are being done in different places to be later on combined. So you also need to have fast links. So when technology is increasing this speed, then there's also research to increase the speed between these links. So that is distributed computing. Now, from distributed computing, we come up with what is called cluster computing. Now, this clustering is the next step in the evolution in the field of computing. So remember, we've started from mainframe. We've moved to parallel computing. We have now moved to distributed computing. And now we are talking about clustering. So computer clusters is made of multiple nodes of computers which perform similar tasks, homogeneous, connected via a network. So you can see with the clustering, we are taking the distributed computing concept a step further. But in clustering, the tasks, you see in distributed computing, we have different tasks. But in clustering, we have these nodes produced doing the same tasks. So execution of a task can be faster as it can be distributed and executed in parallel across multiple machines inside a cluster. All nodes of a cluster together give the impression of a single system. So in a cluster, you didn't know that sorry, what did I want to say? You will think that it's one computer. So you have a job, but you think this job is being done by many computers, but you think that it's done by one computer. So this is a very simple example of a cluster. But one computer is designated as the cluster head. Now, these other computers are performing similar tasks. And of course, in a cluster, we need a local area network to distribute jobs concurrently. So what will happen is when a job appears, the cluster head is going to take that job and is going to split it into 4 parts, where one part is being done by this, another part by this, another part by this. And of course, that is possible because of the network. So each of them performs the job. Then they take the results to the cluster head. The cluster head puts the results together and gives a unified response. The idea was to create a cluster or a group of homogeneous similar computer systems performing similar functionalities. So in each cluster, one computer is assigned the job of controlling the cluster, and it's known as the cluster head. Now, the responsibility of the cluster head in such a simple cluster is to divide and distribute jobs among different nodes in that cluster when matching computing tasks appear. So this is a very simplistic view of a compute cluster, but it's just explaining the concept. Now, in an actual cluster, multiple clusters are linked together through a LAN. Each cluster is built to perform a different type of functionality. In such a computing environment, when a particular job appears, the cluster head divides and distributes it among matching clusters, which are designated for those jobs for fast execution. Now, the distribution and assignment of the job depends on the nature of the job. So in this way, the cluster head starts to utilize the resources in a clustered computing environment. So this is an example. So this is one cluster. This is another cluster. This is another cluster, another cluster. Now, the notable thing is that each cluster is designated to perform different tasks. So this cluster performs an A-type task. This cluster performs a B-type class. This cluster performs a C-type task. Now, of course, because this is cluster computing, you shall find that each cluster has a cluster head. But now, different clusters perform different types of tasks, and later on, these tasks are aggregated and they give a unified result. So that is cluster computing. So cluster computing emerged as a result of progress in multiple technologies and their convergence. So which are these technologies? One, the low-cost microprocessors. 2, the high-speed network communication, and 3, the emergence of software to manage cluster distribution. Now, why is the software needed? The software is needed because it's the cluster head. So that software, ideally, once we designate one computer as the cluster head, that is where that software resides. So the job will always come, a new job will always come to this cluster head. Now that software is the one which is going to do the distribution. First of all, the segmenting of jobs into tasks, and then the distribution of tasks, and then after the results have come, the aggregation of the tasks. So depending on the type of job, I mean, if it's a complex job with different type of tasks, then those different types of tasks will be distributed to different types of clusters. So a set of computers were reserved to handle specific type of tasks to make the system more reliable. If any node fails, other nodes in the cluster can handle the load. The idea behind resource pooling that technologies were trying to implement meant that clustering of nodes opened the path for creating pools of resources. Now, why pools? Is because of what is called redundancy. In other words, if any of these nodes fail, the cluster should continue operating. So redundancy simply means putting in something extra, which under normal operations, it's not being used. It only becomes useful when there is failure. But under normal operations, it's not being used. So for example, one of these computers could be redundant. It's there in the cluster, but it's not doing anything. But in case any of these fails, then it takes over some responsibilities. That is what we mean by redundancy. So from cluster computing, we move to grid computing. Now, the cluster architecture led to more powerful and reliable computing systems by creating resource pools. Now, what happens in a cluster? You mean you could add your computer to a cluster, even though it's not needed. Now it only becomes useful when there's failure in any other node. Now, but it raises concerns regarding its dependency on the cluster head. Remember, we've talked here about the emergence of software to manage cluster distribution. So this is where that software will reside. Now, supposing something happens to this computer. Now, and remember that this is a network. So supposing there is no power on this computer and the clustering software is on this computer, then it means that this cluster is not going to work. So we have a single point of failure. So say for the cluster architecture, performance was largely dependent on the efficiency and the accessibility of a cluster head. So all along, as I've been talking, you can see that we are solving a problem, and once we get a solution, another problem arises. So here we are trying to solve the problem of fast computation. But even as we solve it, we solve it by introducing the concept of clustering. But you see, once we create a cluster, there's an additional problem which is called the single point of failure. So a cluster, yes, you solve the problem of pooling of resources, redundancy, and so on. But you've now introduced another problem, which is called the single problem of failure. So to avoid this problem, or to deal with this problem, we now remove the concept of the cluster head. We don't want a cluster head. We want all these systems to have the same priority. So each node belonging to the cluster would have the same priority. All nodes could perform similar functions, and no particular node had to be assigned the role of head among them. So basically, what we are doing is this. We are going to have the same software in all the computers. So any computer can be designated to be the cluster head. Or rather, in other words, there's no computer that is going to distribute jobs. All computers have equal priority, and they perform autonomously. So as you can see in this diagram, this is now what we call grid computing. So you shall find that each grid performs a different task. Somebody may want him to. Question. Okay. Thank you very much, Edward. Sorry, Naike. Okay. So fine. Anyway, I'm just winding up. I'm winding up. Sorry, I got carried away. So basically, that's the concept of grid computing. So just to wind up, I've actually talked about and the cluster computing. Is that grid, we don't have a cluster head. Two, grid, the tasks can be, the computers can be heterogeneous. They don't have to be homogeneous. They can do different tasks. So I think I'll end up there. You can wind up, you can read this and wind up. Now, just before you leave, a makeup class. Friday afternoon or Monday afternoon, which one would you prefer? Or would you want to discuss and get back to me? Monday.
Yes, we'll discuss and get back.
Okay. So please get back to me early enough. If it's Friday afternoon, get back to me early enough, or Monday afternoon, so that I want to catch up with what the lost